So there's that, and then we can bring this guy back. Okay. So we are getting close to the end. Oh, wait, today's the 13th, not the 12th. And we are through the weeds with all that power series stuff. So, congratulations, pat yourselves on the back. If you need a little bit more time to work through the power series homework in WebAssign, that's okay, just let me know. Sorry, my hair's all crazy. But we are ready to transition to the last couple topics for this class. And usually I spend about 1 week on each. So we are actually right on schedule despite all this crazy coronavirus bullshit. So the plan is to spend about a week talking about polar coordinates and about a week talking about parametric curves. And then those are the last 2 topics. That's it. That's the end of Calc 2. It looks like the one person I had here unjoined. So I guess I'll give just a minute for folks to find that link again and come back. My Zoom originally, when I opened it, crashed. So that might have kicked some folks out, and that kind of sucks. But yeah, that's what we're going to do. We're going to talk about polar and parametric curves over the next few days. I'm going to update this announcement to let them know my Zoom client crashed. I guess if nobody comes back in the next minute or 2, I need to just keep moving with the lecture anyway. You guys can watch the video. So depending on the quality of your trigonometry and precalculus classes, you may have seen these topics before. Ideally, I'm not introducing any of these, but I know that the world we live in is not an ideal world, so I'm going to pretend as though you've never seen or heard of these things before. In each one of those sections, we're going to kind of get used to the new system, because each of them is kind of a new system, a new way of thinking about things. And then we're going to start talking about doing calculus within that new system. I've been working with the notation of my trigonometry textbook, so I want to make sure that I don't steer you guys wrong. Oh, do we start with parametric equations, actually? Yeah, my bad. I swapped these around. So this is 10.3 and 10.4, and this is 10.1 through 10.2. That's actually convenient because I was thinking, hey, maybe we should do parametric curves first. They're a little more important. Yeah, so we will. So we'll start with parametric curves. Basic idea behind a parametric curve is that instead of having y be a function of x, so like my graph is forced to look something like this, you know, passing the vertical line test, or x is a function of y, my graph is forced to look something like this, passing a similar version of that test, but rotated 90 degrees. I would like to look at curves that aren't constrained in any way by a function relationship between the two geometric quantities x and y. So I want to look at curves whose graphs where x isn't a function of y, but nor is y a function of x. And you might say, okay, well, I know some things like that, like the equation of a circle or an ellipse or a lemniscate. There's lots of things like that that we've seen. Cardioids, limicons, you may remember from previous classes. But what I'd like to do is I'd like to be able to stay in the Cartesian coordinate setting, in the XY setting, still be able to work with function notation because of how useful it is when we're doing calculus to be able to treat things as functions, but not have either of my coordinates be a function of the other coordinate. So this is a real challenge. And the trick is to let x be a function of some new variable, I'll call it t, and y be a function of that same variable t, but neither of them being functions of each other. And this new variable t we call the parameter, hence the word parametric. So that's the basic idea. I am curious as to why there isn't anybody at all here. Something needs to be wrong. This is the meeting ID. Jesus Christ, no. Why would that default to open the last thing? That's so dumb. (1372), even if it's encrypted. 1372. Okay, that's it. I don't know. The meeting ID and links are correct. Maybe just nobody wants to wake up this morning. That's okay. I'll post this to YouTube when it's ready. Hopefully that'll be enough for you guys. So yeah, this is the basic idea. So I often graph functions where y is a function of x, or where x is a function of y. We've done lots of this. I want to look at some curves where neither of those things are necessarily true, but I'd like to continue to be able to treat each variable x and y as a function of time. There's several skills that we want to develop here. One of them is taking a curve that's given to you as a function and writing it parametrically. And then another is going to be taking a set of parametric equations that are given to you and coming up with a picture of the curve. So I'd like to get a feel for each of those skills. There are several kind of classic examples. Maybe we'll start with something recognizable. So we'll say graph the parametric curve. X of t equals t squared minus 2t, and y of t equals t plus 1. And since this is our first example, I'm going to do this kind of the most naive way possible. I'm just going to start plugging in points. So if I just start plugging in points, meaning I plug in values for t, my table is going to look like this. Normally, along with the two equations, we'll get some time domains specified. We usually think of the variable t as representing time. The particular example I'm drawing from right now doesn't specify a time domain. So I can plug in any numbers I'd like for t. But if they said graph this curve where t is, 0 is less than t is less than 1, or where negative 10 is less than t is less than 10, then I would restrict the t values that I plug in to whatever the restriction they gave me. But let's start with like negative 2, negative 1, 0, 1, and 2. Just make life simple. When t is equal to negative 2, x of t is x of negative 2. That's negative 2 squared minus 2 times negative 2. Negative 2 squared is positive 4. And then I need to subtract from that 2 times negative 2. So it's going to be 4 plus 4. That's 8. And y of t is negative 2 plus 1 is negative 1. So the first ordered pair that I would graph as I draw this graph is going to be 8 comma negative 1. When t is negative 1, this fellow right here will be negative 1 squared minus 2 times negative 1. So that's positive 1 plus 2. What is that, 3? And then y of t will be negative 1 plus 1, that's 0. When t is equal to 0, x of t is 0, and y of t is 1. When t is equal to positive 1, this will be 1 minus 2 times 1, that's negative 1. And y of t would be equal to 2. And when t is equal to positive 2, this fellow would be, let's see, is that going to be 0 again? That's 4 minus 2 times positive 2 is, 0 again. And this fellow would be 3. So if I come over here to my xy plane, and I mark off some values, it looks like my x values are going to have to run from negative 1 up to 8. So maybe I'll mark this as negative 1, and then 1, 2, 3, 4, 5, 6, 7, go a little further to get out to 8. And then my y values need to run, looks like from negative 1 up to 3, so we'll just start there, call this negative 1, 1, 2, 3. And we'll start plotting. So I've got 8 comma negative 1, that's this guy. And then I've got 3 comma 0. That's this guy. And then I've got 0 comma 1. got -1, 2. And then 0, 3. And I might have a feel for what's going on here. But if I wanted to get a better feel, I could evaluate at 1 or 2 more t-values, like 3 and 4. So when t is equal to 3, this is 9 minus 6 is 3. And this is 3 plus 1 is 4. When t is equal to 4, this is 16 minus 8 is 8. And this is 5. So I'd have to extend this up a good little bit. 3, 4, 1, 2, 3. So this is going to be up 1. 3, 4 is like right here. And then 8, 5 would be right about here. So now you really can see what's going on. This is like a sideways parabola, and it was drawn going from here to here, right? Lower t values started over here, higher t values ended up over here. So if I was thinking of this curve as being traced over time, because remember we usually consider the variable t to be time, it's being drawn in that direction. So it starts down here, and we always indicate, this is called the orientation of a parametric curve, by putting some arrows along it. Okay. So what do these parametric curves look like in general? This is one particular example, and we just made a table of values to get a graph. We noted that as t increased, like down here, this was t equals -2. This guy came from t equals -1. This guy came from t equals 0. This guy came from t equals 1. This guy came from t equals 2, t equals 3, and t equals 4, respectively. So as the values of t increased, this curve was sketched like this. Like this point came first, then this point, 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 then this point. They came in an order, and that's what gives the orientation. So if you think of this t parameter as being time, then you can think of this curve as being traced by a particle in motion. It started down here at when t is equal to -2, and then as time went along, as t increased, the particle moved along this trajectory. And that's one of the main applications of parametric curves in physics, is very, very useful for thinking about particles in motion. So generally, we think of parametric curves as paths traveled or traversed by a moving particle. The orientation, which is indicated by the arrows, is the direction the particle is moving. As time increases. Time, remember, is the thing that we think of the variable t as representing. Now, this last example happens to satisfy the condition that x is a function of y. It doesn't satisfy the condition that y is a function of x, but in general, they needn't satisfy either. And so these curves could look like anything. For us, they will be usually continuous and orientable. But maybe I start down here at time t equals 0. And so this would be the point x of 0, y of 0. And they'll wiggle around and do all sorts of weird, crazy things. And then they'll end up over here at some terminal point. You know, maybe I should call this, instead of t of 0, call it t of a. I'll end up down here at some terminal point, x of b comma y of b, because t is equal to b down here, and the orientation is as I've drawn it. So here I'm thinking of the time interval as being the interval AB. So this is the graph of x equals x of t, y equals y of t, where a is less than or equal to t is less than or equal to b. So in general, these curves can look like anything. Y doesn't need to be a function of x doesn't need to be a function of y. They have an orientation, which is indicated by the arrows. They have a starting point and an ending point. Sometimes this is called the initial point, starting or initial point. And it's the point on the curve associated with the smallest t value in your time interval. And this is called the ending point or terminal point. And it's the point associated with the largest time value, t, right? Here, t equals b. Oh, sorry, extra alarms going off. Shoosh. Boy, I wish I could sleep till 8:30. I said close, goddammit! Great, now my phone is freezing. Technology is rebelling against me this morning. All right. Okay, so this is the basic idea behind a parametric curve, and this is one nice, simple example that we can graph just by building a table. If you have any questions about these particular things, you should rewatch the last few minutes of this video and make sure that these things sink in for you. This last guy didn't have a starting point. This particular example didn't have a starting point or an ending point because they didn't specify a time domain. But the next few examples we'll look at will. Another kind of classic example of a parametric curve is if I let x of t be cos t and y of t be equal to sine t. Now, any number of time domains could be relevant or interesting here, but the one I'm going to play with for now is say from 0 to pi. And in order to get this graph, I'm not going to build a table. I could build a table just like we did on the last example, and that would work out just fine. But I know that if I start feeding numbers into those trig functions, even in the best case, if I feed those nice numbers that I know from my unit circle, the outputs aren't especially nice. They're definitely not integers. And so instead, maybe I should try to do something else to find the graph. So to find this graph, I will eliminate the parameter. And this is a major technique. So we're going to do some algebra to those two equations in hopes that we can find a way of getting rid of the t's and turning this into an equation, instead of having two different equations involving x and t and y and t, into a single equation just involving x and y. And the observation here, I would say, recall that cos squared of t plus sine squared of t is always equal to 1. All right, that's that Pythagorean identity. So if I take x of t and I square it and I add that to y of t squared, I'll always get 1 because x of t is cos t, y of t is sine t. In other words, this graph is the same as, or is the same as, a portion of, and I say a portion of because I have this restricted time domain, the curve x squared plus y squared equals 1. Remember the t's here, this is just function notation. I write the x of t to remind myself that x is a function of time in this setting. But it's still just x that's being squared here, and it's still just y that's being squared there. I just write the of t's to remind myself that they're functions of time. And this guy, of course, is the unit circle. Right? X squared plus y squared equals 1. That's a circle centered at the origin of radius 1. So my curve right here, x of t equals cos t, y of t equals sine t, where 0 is less than or equal to t is less than or equal to pi, is some portion of, because of this time restriction, the unit circle. What portion? So let's find our initial point. Then I'll have x of t, x of 0 rather, because t is 0, is cos 0 is 1. And y of 0 is sine 0, which is 0. So if I label this point out here as 1, 0, that's my initial point. As t increases, x of t decreases, right? The cosine function, if you start at t equals 0, he starts off going down. And the sine function, if you start off at 0, he goes up, right? Picture each of these graphs on their own. Cos of t is a cosine wave. He starts at the top and he goes down at first. So the x value should start off decreasing. And the y value, since sine of t starts off increasing, should start off increasing. So we should be coming in and up, which means that as I start to draw this thing, we're going up like this. I know it's going to be some portion of the unit circle. The question is, from this initial point, do I go up or down? What is the orientation? And then I'll also go ahead and find the terminal point. When t is equal to pi, we have x of pi, which is the cos of pi, which is -1, and y of pi is the sine of pi, is 0. Did I post that to like the wrong place or something? Oh shit, I'm so stupid, I did. I see. I knew something had to be wrong. So people will probably start showing up now. In any case, the terminal point here, for those who are rewatching the video, is going to be at -1, 0. So that's a symmetric point over here. And so we trace the unit circle looking something like this. We arrive over here. And since t is just running from 0 to pi, and these are both periodic functions with period 2 pi, I expect that I'll get only half the unit circle, and that is the case. I'm going to stop the recording for a second. Share, come out of this.